Every time you fly on an airplane, there is one small detail that most people never notice. The windows. They all have the same shape, small, smooth, and perfectly round. But have you ever wondered why? Why aren't airplane windows square like the windows in your house? Or rectangular like the windows in a car? After all, square windows would actually give passengers a better view. Yet engineers around the world insist on making them round. And the reason isn't about comfort, it's about survival. Because decades ago, airplanes actually did have square windows, and the results were catastrophic. To understand why modern airplanes use round windows, we need to go back to the early days of jet travel and discover one of aviation's most important engineering lessons. The yearly Jet AG-110-30 Fibbies, the world was entering a new era, the age of jet-powered passenger aircraft. One of the most advanced airplanes of its time was the British jetliner known as the de Havilland Comet. It was revolutionary. It could fly higher, faster, and smoother than any passenger plane before it. Passengers loved it. Airlines rushed to buy it. And aviation seemed to have entered a golden age. But there was a problem, a deadly one. Within just a few years, multiple Comet aircraft suddenly broke apart in midair. Without warning, entire planes were destroyed, and no one initially understood why. The aircraft had been carefully designed, extensively tested, and approved for flight, yet something was causing the structure to fail at high altitude. Investigators began examining the wreckage, and what they discovered changed aircraft design forever. To understand the problem, we need to understand what happens when an airplane climbs into the sky. At ground level, the air around us presses against everything with normal atmospheric pressure. But as an airplane climbs higher and higher, the air outside becomes extremely thin. At 35,000 feet, the outside air pressure is only a fraction of what we experience on the ground. Humans cannot survive in that environment, so airplanes use something called cabin pressurization. This system pumps air into the cabin to maintain comfortable pressure for passengers. But this creates an enormous difference in pressure between the inside and outside of the aircraft. Inside the cabin, the air is pushing outward, constantly. Imagine inflating a balloon. The air inside pushes equally against every part of the balloon's surface. The same thing happens inside an airplane. Except instead of flexible rubber, the pressure pushes against a rigid metal fuselage. Every flight creates stress on the aircraft structure. And every time the plane climbs and descends, that stress cycle repeats again, thousands of times, over the lifetime of the aircraft. The problem when square windows, 538 knot. Now here's where the shape of the window becomes extremely important. The early jetliners like the Comet had square windows, and square shapes have something engineers call stress concentration. When pressure pushes against a square opening, the force becomes focused at the sharp corners. Those corners act like weak points in the metal. Over time, microscopic cracks begin forming there. At first, they are invisible, but with each pressurization cycle, those cracks grow slightly larger and larger, until eventually the metal can no longer withstand the pressure. In the case of the Comet airliner, investigators found that cracks had started at the corners of the square windows. The repeated stress from pressurization caused those cracks to spread to the fuselage. Eventually, the aircraft structure failed catastrophically during flight. The plane literally tore apart in midair. This discovery shocked the aviation industry, but it also provided a critical lesson. Aircraft windows needed to be redesigned. Engineers quickly realized the solution was surprisingly simple. Change the shape. Instead of square windows with sharp corners, use rounded windows with smooth edges. Why? Because round shapes distribute stress evenly. When pressure pushes against a circular opening, there are no sharp corners to concentrate the force. The stress spreads smoothly around the entire edge of the circle. This dramatically reduces the chance of cracks forming in the aircraft structure. It's the same reason why many pressure vessels, pipelines, and submarine hulls also use rounded openings. Nature itself follows this rule. So bubbles, planets, and droplets naturally form rounded shapes because they distribute pressure evenly. Once engineers switched to rounded airplane windows, the problem of structural stress at window corners disappeared, and modern aircraft became dramatically safer. Modern airplane windows, 10-30-13 Hydros and DAS airplane DARS. Today's airplane windows are even more advanced than early designs. Most commercial aircraft windows are actually made of multiple layers, typically 3 panes. The outer pane faces the extreme cold and low pressure of high altitude. The middle pane acts as a backup safety layer, and the inner pane protects passengers and prevents accidental contact. You may have also noticed a tiny hole near the bottom of airplane windows. That small hole serves an important purpose. It allows air pressure to equalize between the window layers. This ensures that most of the pressure difference is handled by the outer pane. It also prevents fogging and helps maintain the structural integrity of the window. Combined with the rounded shape, this multi-layer design ensures airplane windows can safely withstand the enormous pressure differences experienced during flight. And remember, modern airliners may go through tens of thousands of pressurization cycles over their lifetime. Yet thanks to this simple engineering change, airplane windows remain safe and reliable. So the next time you sit beside an airplane window and look out at the clouds, take a moment to notice its shape. That small rounded window represents one of the most important lessons in aviation engineering. A lesson learned through tragedy, but one that ultimately made flying safer for everyone. Sometimes the smallest design decisions have the biggest impact. A simple curve, a smooth edge, a round shape. That tiny detail helps keep the entire aircraft structure strong enough to withstand the extreme forces of high-altitude flight. And it ensures that millions of passengers can travel safely across the world every single day, all thanks to a window that isn't square, but perfectly round.
Let's look inside this unit. This cross-section reveals the three-pane design: an outer pane, a middle pane, and an inner pane, each separated by spacers for insulation, and improves energy efficiency.
Die shaking will stop. Please, Betzbrock. Whoa, that turbulence is getting bad. With wing flexing like that, it's bending so much it's unreal.
Okay, the results are in. Let's check the lift-to-drag ratio.
Looks good. Drag is down 4%, just as we predicted.
Excellent. Let's run the next iteration. Wow, the sunset is stunning from here. I have to get a photo. Perfect, got it. Look at the frost on this wall. That's from poor insulation, let me show you. See? Multi-layer glazing and gas interlayers keep it warm. No more frost or heat loss. This multi-layer glazing provides frost-resistant insulation for aircraft cabins. A pressure difference causes air to move through the gas-filled interlayers. This flow helps higher pressure temperature and prevent frost, maintaining cabin comfort. In the cabin, pressurization insulation resists frost while maintaining clarity. This system maintains circulus pressure, ensuring passengerable flight. Aircraft cabin pressurization maintains a safe, comfortable environment at high altitudes. The aircraft structure remains stable and safe, with systems continuously pleasuring in passengers. Cabin pressurization is vital for passenger comfort at high altitudes. Fresh air is circulated continuously to maintain oxygen levels. This ensures a safe and pleasant flight. Rounded window designs minimize metal fatigue by reducing stress concentrations. In contrast, sharp corners create high stress points, leading to fatigue and potential cracks, preventing failure and enhancing durability. Okay, let's check this section of the fuselage. Right, I'll scan for any dents or scratches. This panel looks clean. Good, mark it and let's move on. Copy that. Windows all check out? Yes, all seals are secure, no cracks or distortions. Good, let's get a closer look at these rounds. Right, the shape is perfect, no warping at all.